And then if I have circulating charged particles, so what happens is because of the way these magnetic fields work, I can send a charged particle into a magnetic field and it's going to end up going in a circle, right? And so, QVB sine theta, QV cross B, that's what we end up with as the force. And so if we have something that's ending up going in a circle, right, in a magnetic field, then the force is a centripetal force. So we have another type of centripetal force, so that ends up being QVB equals mv squared over r. And when we solve, if theta is 90 degrees, right, then we end up with QVB equals mv squared over r. And so that ends up being r equals mv over qb. The way that I remember this, I don't know why, but it just sticks in my head. I tried to come up with something, and I come up with read my very quotable blog. I don't have a blog, and if I did, I don't think it would be very quotable, but that somehow is in my head. Read my very quotable blog. So it helps me remember that equation. And that's important because we're going to be seeing a lot of this type of thing where we've got particles going into a field and then it turning, and so we're analyzing what happens to the radius of the curvature as it's going in. And so in example 7, we want to know the paths of these various charged particles of equal mass when they enter the uniform field. So equal mass is important because equal force on equal mass is going to produce an equal acceleration. And so those are going to produce, if the charge is the same, also, because that's important in this equation, different radii for the particles here. And so the first one, that'll be this one, this positive particle coming in. The positive particle is moving this way, right? And this is coming, the magnetic field is out of the page. That's going to produce a vector down, right? And so it's going to end up having, it's going to curve back down around underneath, right? This one is a negative charge. So you reverse the direction of the velocity, and then B is coming out of the page, so that's a force upward. So that's going to produce that type of motion, right? And then this one, this is a negative charge, so again we reverse. Here the field's going into the page, so it's like this way into the page, it produces a force downward. For this next one, notice it's two negatives. So I am doubling the charge. If I double the charge, that means I cut the radius in half. So whatever you made as the radius of this path, cut that in half, and that'll give you the radius for this one as well. Okay, and you can count that just in terms of these kind of like grid lines almost. Okay, and then in example 8, all you're doing is you're taking that read my very quotable blog equation, and you're substituting in, if you have 2q, then that cuts the radius in half. And you're saying if this is going to be clockwise or counterclockwise based on the information, right? It's the same uniform field directed into the paper. And so you're imagining this particle coming in kind of like this one, right? It's coming in, but since it's into the paper, positive Q would be that way into the paper, so it would produce up. That would be a counterclockwise, like this one, right? B is into the paper, V is going that way in, up, so that would produce a counterclockwise radius going that way for this first one. Positive 2q, same direction counterclockwise, except that now the radius is cut in half. Now negative 2q, so this is going to produce the opposite direction, like this one, right? But it's 2q and 3m. The m is on top, q is on the bottom, so it's going to end up being 3 halves. 3 halves are clockwise. Ooh, see that? And then this next one, 2q, 2m. So those cancel out, but there is still the v. So it's twice the radius, but it's positive, so it'll have a counterclockwise path. This one is negative q, but 3v, so it's 3r, right? The v is up top, so if you multiply 3 times v, then you have to have 3 times the radius, 3r, and it's negative, so it'll be clockwise, just like this one, right? In a magnetic field going into the page. And then here, negative 3, 4, and 2. The q's on the bottom, the 4 and the m and the v are both on top, so you end up with 8/3 r, 8/3 are and this one's clockwise because it's negative, just like this one. So going down the radii are r, half r, 3/2 r, 2r, 3r, and 8/3 r. And then all the positives are counterclockwise, all the negatives are clockwise. And what can also happen then is we end up with these circulating charged particles, where it's given just a little bit, like these are circles, so these are coming in and they are perpendicular, the velocity is perpendicular, but if the velocity is also directed into the page a little bit, that piece that's parallel to the magnetic field, there's no force on that, so it's not going to accelerate. And what you end up with is these helical paths. These are not spirals. Spirals, by the way, spirals is where the radius gets smaller, right, so it gets closer in. Something going at a constant radius but moving along like that is a helix. And so that's why for the gene they say DNA, it's a double helix. Spiral staircases are mostly actually helix staircases. So anyway, you can end up with this type of path, and then also you can see that you can have magnetic bottles. Right? So by manipulating the magnetic field, if you have charged particles in there, you can hold those charged particles in place without ever having to touch them, just by creating and manipulating the magnetic field. And that's really useful for things where they're doing nuclear experiments and they have very, very, very hot substances, so hot that if you put them against any other substance, they would melt them. But you can hold them in place away from other things by producing a magnetic field. And so that's it for our introduction to magnetism.